So you're dealing with liquid structure in the last class. So continue from there, and just some recapitulation. We started somewhere here. Okay, so I have a classical system. The Hamiltonian of the system is given by this. It depends on 3n position coordinate and 3n momentum coordinates, and together I'm calling it r to the power of n, which basically means r would have like x, y, z components. So actually have 3n position coordinates, and similarly 3n momentum coordinates to the power of n. And the Hamiltonian, you can split it into two parts. One is kinetic energy, which is very simple, which is like p square by twice m sum over all particles, n number of particles. And then your potential energy, because this potential energy is actually how these particles interact with each other, and usually it is pairwise interaction. That is how it is treated. So then you can calculate this partition function, which is kind of which I'm calling classical partition function, but assuming the things are indistinguishable. So you have n factorial, and I divide by h to the power of 3n because you have to take care of the dimension. And essentially, our integral of this exponential of minus beta h, this Hamiltonian, integrate over all position and momentum coordinates. Okay. Then we define something like this f, which is the probability distribution for observing a system, classical system, at phase point r to the power of n comma p to the power of n, and this is given by this, and this can be split into two. One is the momentum part, other one is the position part, the configuration part. Okay, it is done, and I'm more interested in this part, this p of r to the power of n. This is the probability distribution for observing the system at a configuration space point r to the power of n. Okay, and then you have defined this reduced configurational distribution function, the p2 by n r1 comma r2, which basically means I fixed two particles r1 and r2. These particles are also fixed, so as a specific, so it is called specific probability distribution. So I just have to integrate this quantity over all the position coordinates or the configuration coordinates other than r1 and r2. But this is for a specific two particles in an n particle system. Then we did more generic thing. Then we define something that not specific but any two particle. In that case, there will be factor of n factorial by n minus 2 factorial here, times this p of 2 slash n r1 comma r2. Similarly, you can define even a more generic distribution, general probability distribution, which is like rho to the power of small n slash capital N. So I choose any small n number of particles from a collection of capital N number of particles, classical particles, and I know the prefactor is going to be n factorial, capital N factorial, divided by n minus small n factorial, and then I'll have this, whatever this p of this distribution. Okay, and the denominator is like a partition function, but this is the integral over the position coordinate. This is called configurational integral, and I denote this with something like z or zn. Okay, and then we have defined this. This is the definition. Essentially, is following from the previous slide, that this distribution is given by this expression, and this is the expression which I'm going to use today. And we had showed that if you take this integrate over all the position coordinates of the particles which you have tagged from 1 to small n, then you get this n factorial divided by n minus n factorial. Okay, and if you do it for a single particle case, then it is actually equal to the total number of particles. Okay, and we also had done few other things from here. We had shown that for ideal gas, this is equal to rho square, and also for the liquid, we had shown that this is equal to rho square times g of r if you have a homogeneous liquid. And I think we had stopped here, and then I showed the distribution function, this g of r, this pair correlation function which is defined here, and g of r is actually gives you a picture of liquid structure. So liquid structure is given by g of r. Okay, so today we'll see how to measure g of r experimentally. How can one measure and more about G of R today. So we'll start from here. So for this, I go here. So let me write down this reduced distribution function. You can check your notes. It's already there in the notes. But so this is rho in my notation slash n r1. And since you have 2 slash n, this is for any two particle, and it has to be n factorial divided by n minus 2 factorial, and then you have 1 over this configurational integral, and then you have to integrate over all the position coordinate other than 1 and 2. Of this quantity. Okay, this is something which we're going to use later. Okay, are you following, everyone?
Yes, sir.
Yes, sir.
So let us now use something like a delta function. Now using Dirac delta function. How many of you know Dirac delta function? It is taught in quantum mechanics, I'm sure.
Yes, sir.
Actually, when you integrate Dirac delta function, it has some meaning. Otherwise, it is very weird because it's not really function, because it is defined at a particular point with infinite height, isn't it? And is zero everywhere. So only when it is under an integral, it is multiplied with another function, I integrate, it has some finite value. Anyway, so my point is that this one particle density, this actually I'm defining for liquid state. It is defined as follows, that I take a Dirac delta function which is like r minus ri. I goes from, sorry, I goes from 1 to total number of particles. And so basically, whenever my position of the particle is equal to r, then only I count. Okay, it is like forming a histogram, but this is not the whole story. The whole thing has to be averaged. It's an ensemble average of microscopic particle density. So basically, this is your microscopic particle density. So the whole quantity is the ensemble average okay. This is the ensemble average of microscopic particle density. Okay. Now you should realize this. This is very important. This averaging is important. So what you do actually, as if you are forming a histogram or something, whenever you people are saying something, why don't, okay, yeah. So whenever you take this average, for example, what is this? This basically means that I have many particles, n number of particles. I just look at a snapshot. Some particle are somewhere, okay. And I ask you what is the probability of finding a particle if I start from origin at a distance r, radially r from that origin. There's a particle at origin, I sit on that particle, and what is the distance of finding, what is the density at a distance r from that origin, okay. So basically I have to count all the particles who would come there. So you'll have different snapshots, you understand, different snapshot, and I have n number of particles, so any of them can be found at a distance r from center. So that's why it's a delta function. This function has a value. It's a huge peak value when r equal to ri. So I'll take that, and then I'll take a sum over all possible sum over all the particles, n number of particles, and that is not enough. Then I have to sum over all possible arrangements. That is this angular averaging. So it is like ensemble average, because your n number of particles, but n number of particles are indistinguishable, but you have many such snapshots. So you have to take average over all such snapshots. It is like ensemble average, and this is how this single particle density is defined in statistical mechanics. Okay, so this is very important. So this is the essentially this is exactly what we did, but not using delta function in the last class. So let us consider another quantity. The quantity is like this: delta r minus r1 delta r prime minus r2, the product of two delta function and average. What should I write on the right hand side? This average is taken over this distribution, no, this configuration space distribution. So it is going to be something like 1 over Zn, and then I should take this, and then I should what should I do? I should multiply this with exponential of minus beta u, which is a function of r1 r2 up to rn, and then I integrate over. So basically this basically means integration over all position coordinates. Is this clear to all? The definition? This is averaging. How do you average? Just look at it.
Yes, sir.
So you have to practice, otherwise it is very difficult for someone to follow this class. So this is how you average. You multiply it with this, integrate over all space, but also divided by this, isn't it? How do you do an averaging? Average of any quantity, say average of x. You do what? X times xi times pi I. And if it is integral, then you do like this, no? Isn't it? Divided by, of course, you do. So this integral px dx is zn, because zn, you remember what is the definition of zn? Is configuration null integral. Okay? I don't think you have a problem with this. This is fine? Is this fine? Look
Yes,
at
sir.
the structure. Look at the structure. Now look at the structure means look at this expression. I have this expression. Okay. Now this factor is equal to n into n minus 1, no? Okay. This is your two particle density. This is this quantity, the one I've defined here. So but just by looking at these two expressions, just look at these two expressions. Just look at this expression. And then I ask you to calculate a quantity like this, which is delta r minus ri delta r prime minus rj sum over j sum over I. Now I goes from 1 to n, j also goes from 1 to n, but I put a prime here. This prime means what? Can anyone tell me? This prime? This prime.
I equal to j.
Yes. Prime means I don't take I equal to j. Okay. Now if I do this, I have this structure is shown here. What is the structure? Essentially, each term is like this, isn't it? Each term is like this. Each term is like this. Okay. So actually, you can show that this is this quantity is actually what? Can anyone tell me?
Which quantity?
This quantity. Can I write it something? Can I write something? This is equal to something. What is this quantity?
Nn minus 1 into ensemble average of the delta
Yeah,
r
yeah.
minus 1
Okay.
delta
But can
prime.
I can I can I simplify it further? My question is, can I simplify it further? Actually, if you look carefully, this quantity is nothing but your. Can you see that? Look at the structure here. What is this structure? Now this quantity will have many terms. No, how many terms will be there? Can anyone tell me?
Nn minus 1.
So there will be n into n minus 1, no? Into terms like, say, if I call it, say, a. Can you get this? Are you getting this?
Yes, sir.
Yes. So basically, actually, by using delta function, you can also define this two particle density. Is this clear? Is this clear to all
Yes,
of
sir.
you? All of
Yes.
you. Okay, so two particle density is clear. One particle density is clear. So let us calculate something else. Let us calculate something else. I was thinking whether I should do this. I think I should do it. Yes. So now let us calculate a quantity like this. I go to the next slide because it is going to be something. So let us calculate a quantity like, I'll tell you, 1 over n, sum over I equal to 1 to n, sum over j equal to 1 to n, but with a prime. Now delta, just look at it, r minus rj plus ri. Let us calculate this quantity. Let us calculate this quantity. Okay. Now I'll give you one uh, like this one. Okay, I'll do a trick. I don't know whether you understand this. 1 over n is a constant. No, I can take it out. I can take it out, and then I'll integrate this, but before integration I put this in the I goes to 1 to n, uh, j goes to 1 to n with a prime. Now this is delta r prime plus r minus rj. Now delta r prime minus ri. Okay, and of course, and you can put dri, yes, dr prime, and sorry for this. This is something like um, integrate average, then you can put whatever. How many of you can understand this? Have understood this? Use some delta function property. So let us see what I have used. I don't know how many of you understand this, that this can be expressed like this. Anish, can you follow?
I
Can you follow?
No, I cannot.
How many of you can follow?
no sir.
What is a delta function? Tell me.
Peak at say one single position.
But you have to know about delta function. First of all, if
So
I take a delta r,
I was just saying that you can just replace this r dash with ri from right hand
yeah,
side
yeah,
to
yeah, yeah. So if I integrate this, this is 1. Okay. And if I have a delta r minus say r prime, dr prime, what is the answer?
Again one.
Again 1. Again 1. What about this? Fr into delta fr fr delta r minus r prime del r prime integration. What is the answer?
FRR prime.
This is f for r prime. No, it cannot be f for r prime. We have integrated over f r prime. How can it be f for r prime?
FR then FR.
Yeah, it is going to be fr. It is general r. So similarly, I have used some delta function property here and written this integral as a product. As I, for example, I integrate over dr prime. Okay, how many places dr prime are there?
2 places.
Can you see that? Can you see that you can do it? How many of you can do see that? See, if I integrate over dr prime, so what will happen? Wherever I have dr prime,
Yes, sir,
r
I can
prime,
see it.
that will be replaced by ri, isn't it? That will be replaced by ri. So this one you can write it as this product. Okay, leave it. This product I can write it as something like, it is a function. Let me write down this function of r prime plus r minus rj delta r prime minus ri del ri, sorry, del r prime integral. Now tell me what is the answer if you know this. What should the answer?
Delta Rj minus R.
Kailash, what is going to happen? I am going to integrate over delta r prime, no, r prime. So I should replace r prime with rj, ri. Whenever I get r prime, I replace it with ri. So you should get f ri plus r minus rj. That is the answer, isn't it? Can you see that? It's just like
Yes
this.
Yes.
sir. Yes sir.
And
Yes sir.
what is this f? F is your delta function here. This is f here is a delta function, no? In this case, this is your f. So let me write down here if you don't understand. So as if this is some function, this is a function of r prime plus r minus rj. And this is your delta function, no? So this should be equal to your f ri plus r minus rj, which is nothing but, because if f is delta function, no? And this is exactly what you had here, isn't it?
Yes sir.
So basically, I just use a trick. Now, if I use a trick, what is advantageous here? Can you tell me? The advantageous thing is here is 1 over n. Look at it, what is there in the integral? In the integral, what is there? Not the integral, like, let me tell you. Other than the integral. So I am saying
It,
that, yeah.
it will be non-zero only when r
No,
dash.
no, don't make things complicated. This is 1 over n. And then I have what? I have this.
You can separate out the solution term.
This one I have, no? Exactly this one I have, no? This is the expression. This is the expression. What is this? This is my question. The angular part. Look at it carefully. What is this angular part?
Rho 2 by n R1. In this
Just
case, R1
go to the previous slide.
Rj minus Rn Ri.
This angular part is something like two particle. It is like two particle density, isn't it?
Yes.
But not at R1, R2, but at R prime and R prime plus R. Isn't it? It has to be R prime and R prime plus R, isn't it? R prime and R prime plus R. Can you see that?
Yes, sir.
Let's go to this expression. C is R minus Ri, R prime minus Rj. Here, R prime plus R minus Rj and R prime minus Ri. So basically, you have an integral of this 2 by n R prime. You can put this first, or doesn't matter, though anyway. So this is clear that this quantity is this. Is this clear?
Yes, sir.
Now can I further simplify this? Can I further simplify this? Now if you have homogeneous liquid, you remember what is going to happen. It is go back to your previous slide. You see there are definitions. What are the definition? Go to
All the
previous.
points will be similar.
Yes, but you remember that rho is n by v. Not only that, you also had this the relation between rho 2 slash n and g of r. You remember that relation?
Rho 2 by n by rho square is equal to G
So
R1.
you will have 1 over n. This is there. So this one I can replace this as rho square, isn't it? Integral of g r comma r prime and dr prime. And since I can integrate over dr prime, if it is homogeneous fluid, then I have rho square by n, because this dr integration will give me anyway will give me what? V, and you have rho square by n is there, and then you have this v is actually n by rho. So this is coming from this integration of dr prime, and then you have g of r. So essentially you have rho times g of r. So you have to practice a lot, otherwise it's difficult to practice a lot. So this quantity can be expressed as rho times g of r. Okay, rho times g of r. Essentially the definition of g of r. Can you see that? Essentially the definition of g of r. Okay, this is the definition of g of r. Using delta function. Using delta function, you define g of r. Are you fine with this?
Yes, sir. Fine.
Actually, this is how one can code. Actually, if you do computer coding, you can code. This is essentially a histogram kind of thing. Okay, equal to Ri minus Rj. Whenever two particles are separated by distance r, you take that and you take over sum over all the particles, divide by the total number of particles, and then you average over all the realization. That will give you a g of r times the density. Okay, Anish. So actually, you can show this. You can do this on a computer. You can code it. In our lab, we do that. Okay. So let us now move to some other quantity. But now I have to connect this liquid structure to some experimentally observable thing, something which I can observe experimentally. So the point is that something which is experimentally measured is called the structure factor. And this is measured using X-ray or neutron scattering. Because why X-ray neutron scattering? Because you're dealing with this liquid structure, so the length scale is around angstrom, no? So that's why you need X-ray or neutron scattering. And what is the definition of this structure factor? There is a definition of structure factor is divided by 1 over n, sum over of some density, but in Fourier space, rho of minus k and rho of k average. This is the definition of your structure factor. How many of you have heard about X-ray, neutron scattering? You know that?
Sir. Yes.
Yeah,
Yes.
this essentially you measure the structure factor. Now, what is rho of k? It is a Fourier transform of density. So actually, mathematically, it is given by this. It is dr exponential minus ik dot r to r. Okay, is this fine? This is the definition of Fourier transformation.
Yes, sir.
Let me write down Fourier. Now you remember what is the definition of your rho of r? You remember definition of rho of r? So let me write it down. You'll remember.
Sum of the deltas.
Okay. This is how it is, isn't it? Okay, so now if I calculate this S of k, then if I use this definition, what I'm going to do, I'm going to now when you do this integral, so this will be integral you can do. What I'm going to get a sum over, because using the delta function property, it is exponential of minus ik dot ri. Okay, this is how it is. So your S of k is going to be 1 over n, and I'll have rho of minus k and rho of k. This is rho of k. What is rho of minus k? I have to take minus k here only, isn't it? So I'll have two dummy variables, the summation variables. One is I to n, another one is j equal to 1 to n. Here there is no prime, you see. It is over all possible n. What is the first term? What is rho of minus k? Rho of minus k is going to be exponential of plus ik dot r, isn't it? Ri, whatever. And the plus k is going to be minus ik dot rj. Now I have I and j. So combining this, I can write that minus ik dot ri minus rj. This is clear? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
This is your structure factor. Look carefully. Now I'll have diagonal terms as well as I'll have off diagonal terms. How many diagonal terms I have?
In
N number of particles are there. No, how many diagonal terms?
in
N. No, it is n because in pair.
yes, sir.
You understand? Because whenever 1, 1, 2, 2 like this, no, like this, isn't it? Those are the diagonal
Yes, sir.
terms. Self. This is called the self part. So I can split this into two. The first thing is going to be I have whatever. Okay, and angle you put 1 over n is there, and then when ri equal to rj, what is the value of this? This quantity is 0. Exponential of 0 is 1. And how many terms I will have? Such terms, n terms, isn't it? So I'll have n. Plus I will have I1 to n, I think j not equal to I. to n, isn't it? So this one, the first term is gives you 1, no? You can take it out. Is it fine?
Second term will also have a 1 over n.
Yeah, yes, forgot. This will have 1 over n. Now 1 over n is a constant. I can put it outside also, but if you want, I can put it inside. Okay, this is fine. Up to this is fine. Any problem so far? Now I'm going to make use of again delta function. So what I'm going to do, let me write down. Are you following, all of you? Exactly the same thing I did. What
Yes,
I
sir.
did in the previous slide. Exactly the same thing what I did in the previous slide. Because integration over is from is over r and r prime. Whenever I integrate over r, whenever I get r, that should replace by ri, and whenever I integrate by r prime over r prime should replace by rj. So it will become ri minus rj. This is exactly whatever you started, isn't it? I hope everyone is following. Now look at it carefully. Can you see anything similar that which you have learned very recently? How many of you see something similar which you have learned recently? Anything? What is the definition of rho 2 by n? You remember? Rho 2 by n. You remember?
Object average of sum over I, sum over j not equal to n.
So basically, if I take this
That part.
part, you know, this is something like rho 2 by n, isn't it? Ri rj.
Yes.
Something like that, no? It is like that. This is exactly what I did. Now it is not Ri rj, rather it is actually, you can call it
R prime.
yes, r prime or r minus r prime. Depends on the separation. Depends on the separation. That is how one should do. So I go to the next slide. Sorry for this, but I'll write down the expression for s of k. So your s of k becomes 1 plus 1 over n exponential of minus ik dot r minus r prime rho 2 by n r minus r prime. Why do I put r minus r prime? Any idea? Since we have a homogeneous liquid, isn't it? So it should not depend on Ri and Rj. It rather depends on the separation between Ri and Rj. Isn't it? You understand? It's homogeneous fluid.
Yes, sir.
Your density should not depend on two particle density should not depend on these 2 points. Rather, it will depend on the separation. So if I keep the separation fixed, and then I say the separation 10 in some unit, 10 angstroms. So I tag, okay, I have 10 angstroms somewhere. But at the same, I can have another situation. I can have this 10 Armstrong somewhere else in that fluid, in the liquid. Your density should not change, isn't it? This two particle density. Are you getting?
Yes, sir.
Homogeneous.
Homogeneous and isotropic, isn't it? And isotropic means it depends only on the magnitude, r minus r prime. Okay. So what will happen to the next step? Sk is equal to 1 plus, just look at it carefully. This one you remember, no? This one, the definition of this is equal to rho square g r minus r prime. Remember? So,
Yes, sir.
okay, so I can take that rho square outside. Rho square by n, it will become what? So, and also I can integrate over all one position. So what I'm going to get, when you take it outside, I'm going to get 1 over n rho square and then a volume from one integral, and I'll have one integral less, which is gr. Okay. And this is, and if I write it properly, I'm going to get 1 plus rho is nyv. So v will cancel. Am I doing it correct? Because it has to, there has to be n square by v square. N will cancel. N by v. Yes, you're right. So this is going to be rho, isn't it? It will be n by v, because v rho is n by v square. N square will become n, and this will become v. So n by v. So it is rho. And this is a very important relation. What is this relation? It tells you what is this, what you are doing. You are doing a Fourier transformation of g of r. So essentially a Fourier transformation of g of r gives you what? Structure factor. Look at it. This is the real space structure, but this is what you measure in experiment. Structure factor in the, what is that called?
X-ray scattering.
In X-ray or neutron scattering? Or neutron scattering? So that will give you here. So this is a relation between g of r and s of k. Clear? This is very important. So this is how the structure of liquid, even solid, is determined, isn't it? Now, what is structure factor for ideal gas? What should be the structure factor for ideal gas? Some constant, isn't it? There is no variation in structure, isn't it? Look
Yes,
at
sir.
it. Look at it. So now, up to this is fine. Now, I can now think of, there's something I'm going to talk about a little bit. It's called reversible work theorem in this context. So, reversible work theorem in this context. And I think with that, I don't know, maybe I'll go a little more. So basically, I take two particles. I have n particles, system. And they are separated by a distance, whatever. R1 minus R2 distance. And I have many such particles are there in the system. And I do an experiment. I bring these two particles close to each other, particle 1 and particle 2. They are held fixed at R1 and R2, first of all. Okay. And then I ask, what is the force acting on? Force acting on, let me do it, particle, say, 1. 1 is fine. 1. What is the force? The force is due to all other particles. How do I calculate force?
Medium to potential.
I have to know the potential. The potential is something like u, is a function of all the coordinates. So I have to take a derivative of this with a minus sign. This one. And then I have to take an average over all realization, isn't it? With the condition that R1, R2 fixed. I just keep the distance fixed and I then calculate what is the average force of interaction between these two tag particles due to all other particles. Are you getting my point? What I am doing?
Yes, sir.
Now what is the expression for this? What should I write on the right hand side? This is minus. See, I should integrate over all possible values of all the coordinates, isn't it? Only 1 and 2 are fixed. I should not integrate over 1 and 2. Put, now you know StatMac, no? You should be able to see this.
Yes, sir.
What is the denominator then? It is something like z of n, but I'll not have all the coordinates. I'll have only dr3 to drn, isn't it? Is this fine? Is this fine?
Yes, sir.
Now, look at it very carefully. This one I am writing as kVt del dar 1 Can I write it like this? Tell me, can I write it like this or not?
Yes, sir.
I can, no? Because I know that ddr1 of e to the power of minus beta u, actually it is, what is this? ddr1 of, it is minus beta exponential of minus beta u into, this is how it is, isn't it?
Yes, sir.
This is, so 1 over minus beta into ddr1 of e to the power minus beta u, u is capital U, is equal to e to the power of minus beta u, and this is exactly what I have used here. No, this quantity was there. So let me highlight this quantity. This is the quantity, no? This is the same thing, no?
Yes,
And this one I'm writing it as this. So this minus and this minus will become plus, and 1 over beta is kVt. That is how it is, isn't it? Is this clear to everyone?
yes, sir.
So let us now um, go to next slide. Next slide is like this. Okay. Then this quantity, whatever the quantity is, actually minus let me write down again, kVt, sorry, You understand this, no? What I have written is, and look at it. This one, I can do another trick here. I think I better to use
Derivative
pen.
of log.
Huh?
Derivative of log of
Yes.
dt.
So kVt, I can write this is kVt of dt r1 of log of are you convinced? This is how it is. Are you convinced? This is how it is.
Yes, sir.
Yes, sir.
Now you know that. Let me do it for you. ln x y z is ln x plus ln y plus ln z. This is fine. A stupid thing, but let me do it. Huh?
Yes, sir.
Everybody knows. Everybody knows. So I'll make use of that. So I'm going to do kVt ddr1 of, see, this is taking derivative with respect to r1. So this is a log of something, no? Log of something. Log of something. Um, Here this is little tricky, this step. I'll tell you this step. This is little tricky because what I want to do, I want to just like this one, I can write it as, just look at it carefully, that ln n into n minus 1 into dr3 to drn. Okay. Sorry, I should not be. This slash, this is, okay, slash divided by drn so I do this trick. There's a trick, another trick. So I have log of this, integral of this, all these things, no? This one I'm writing it like this. And the next step is as follows. You can go and check yourself. This is kVt. This is ddr1 of ln g of r1 comma r2. And this one, this quantity I can call whatever, some w. This is like a some potential of mean force. Okay, is minus. So if I write it properly, I'll be, if I assume this isotropic liquid depends on the distance only, is going to be minus kVt. Okay. Uh, like minus kVt, like I think better I write like this, minus uh, ddr1 of something like w r, not r1, say r of in general. In this case, what will be the w? Tell me. This is not w actually. I should have not said w. This is not w. The derivative of that is w. So you understand what I'm saying? What I'm saying that, okay, this quantity, you take a derivative of this, no? You are taking derivative of this. You're taking a derivative of this, no? So I'm calling this quantity itself. Now this should not be w of r. I'm doing so many stupid thing. What I'm saying, say, let us write down. And I can always say there is something like w of r, which is minus kbt ln g r. Okay, where r is r1 minus r2. This is exactly what I mean. Why this is so, Anish? Because, and Kailash also, this is because this is what? This is something like, this is a force, no? This is a force. It's a,
Yes.
it's a negative derivative of some potential of mean force. Minus, this is like, this is my, it is like minus dw, you can call it r by r kind of thing, isn't it? This one. Or you can call it r1 also, because I'm just taking the distance to be r. So this is how it is. So that's why this is called the potential of mean force. So what is the potential of mean force between two particles in a collection of n particles? It is minus kbt times log of g of r. Is this clear?
Yes, sir.
And this is actually the reversible work done in order to bring these two particles, when they are separated by infinite distance, and you bring them to a distance where the separation is r. So this is like irreversible work done, isn't it, in NVT? And that is why it is Helmholtz free energy.
Hello, sir.
Yes.
Sir, here are we neglecting the interparticle force between R1 and R2 particle?
No, we are not neglecting. We are saying that, okay, we don't care what is the interaction between R1 and R2. We are just keeping them fixed. So basically, yes, what I am saying that R1 and R2 are fixed in space. Okay, fixed in space. And this is the interaction actually between R1 and R2, W of R.
Okay,
Yeah,
because it is in equilibrium. That's why
it is
it
in
looks like.
equilibrium. They are fixed in space and separated by distance r. And then I am asking what is the interaction, what is the average interaction force between these two particles which are held fixed in space due to all other particles, due to other n minus 2 particles. The effective interaction between these two particles. Okay, this is called reversible. This is called potential of mean force. And in this NVT ensemble, this is the NVT ensemble. You are dealing it. This is equal to a free energy. This is what is this free energy? Actually, this is your Helmholtz free energy. Are you following? This is Helmholtz free energy. How many
Yes,
of
sir.
you have followed that this is Helmholtz free energy? And here there's a trick you can check yourself. Okay, it should come G of R. It should come G of R. Okay, now let us do few more things. I want to do few more things. How much time I have? I don't have much time, but I try to do few more things. So let us do this. How to model pair potential. So actually, whenever you write this u of r to the power of n, it depends on how many coordinates, n coordinates, isn't it? In general, it depends on n coordinates, no? But the usual idea is that u r to the power of n, which is your the interaction potential, no? How do you write this, Kailash? You write in terms of pair potential, no? So I like small u, and that depends on Ri minus Rj mod of that, and then I sum over I greater than j equal to 1 to n. This is sum of pair potential. Sum of pair potential, that is exactly what you do, isn't it?
Yes, sir.
This is n body potential. And this pair potential, can you give me a good example of this pair potential?
Lennard-Jones potential.
Yes, yes.
Potential.
A good example when you're say, dealing with say not charged, uncharged atomic system is a Lennard-Jones potential. So Lennard-Jones potential is something when you're not charged system, no? Like argon, a collection of say argon atoms, okay? Then it is a good thing to deal with Lennard-Jones potential. And how many of you know the expression for Lennard-Jones potential?
Yes.
How many of you know?
Epsilon sigma by r to the power 12 minus sigma by r to the power 6.
Okay, so let us write down. It's 4 epsilon. This is sigma by r to the power 12 minus sigma by r 6. This part is for what? For
Repulsion.
repulsion. And this part is for attraction. So there will be a balance, no? And if I plot this, how does it going to look like? If you plot this, it will look like this. Isn't it? And what is
Yes.
this? This is your epsilon. This is your 0. This is something like r naught. This is something like 2r naught or something. Okay, this is how it is. Not exact, 2r naught will be somewhere here. So I think I should change it. This is how it is, isn't it? This is your epsilon. And this is your r naught. 2r naught may be here. Like this. What is the value of r naught? Sorry, not this one is r naught. R naught is this one. Where the should not be. How do I calculate the value of r naught? Tell me.
By differentiating and putting it 0.
Okay. So r naught is at r equal to r naught. Your ur is given by minus epsilon, isn't it?
Yes, sir.
And this r naught you can calculate. It is 2 by 1 to the power of 6
6.
times sigma. It is I think 1.12 sigma. No, something like that. Check.
1.122.
Okay, 1.122 sigma. Okay, you check this, slightly greater than 1. This is what? This is the pair potential, as if you have two particles, they are separated by distance r. But you have n particles, no? So each of the pair will interact through this pair potential. And this is how one can model, for example, liquid helium, liquid argon. These are good models. Okay? But in helium and argon, what happens? The attraction is very, very feeble, almost not there. So there is another potential. This is called WCA potential. I'm not going to talk about it now. We can talk later if required. But my point is as follows. Now, if I calculate the average internal energy of such a system, what should I do? You know StatMac very well. Now I can be a little fast. This is fine. Kinetic energy. This is potential energy, no? I have to take average of this. What is this value? Can anyone tell me? There are n particles, n times average of p square by twice m plus this. This is going to be again. Now I have pair potential, the small u, which is a function of. Okay, what is p square by twice m? Can anyone tell me what is the p square by twice m average? Equipartition, you should know. This is, tell me.
1 by 2 kT. Yes, sir, 3 by 2 kT.
This is how it is, isn't it? Plus this. Now let us calculate this. So in order to calculate this, essentially I am calculating this, no? U R I J in general. And how many such pairs are there in the system? How many distinct pairs? Tell me. Kailash, if I have n particle system, how many distinct pairs are there?
N minus 1 by 2.
N factorial.
Good.
Half n, half n. This will be half n.
Good. Anish, how many?
N minus 1 by 2.
Actually, it should be n into n minus 1. But I divide by 2. Why? For
INJ and IJ, J.
yeah. For you should not do double counting. Okay. For not to have double counting, no? How do you get n into n minus 1 by 2? Can Anish explain?
It's like if I have to pick the first particle, I have n choices. Second particle, n minus 1 choices. But then, in order to avoid double counting, you just divide the product
Yeah,
by 2.
that's how it is. So this is how it should be. So this average, I can write it as n into n minus 1 because each term will be similar, no? Are you convinced? This is how it is.
Yes.
It should be like this, no? Where you have n into n minus 1 by 2 number of pairs, and each pair would have energy like this, UR1 to average. Okay. Now, how do you calculate this UR1 to average? Let me write down. Remember the expression for averaging? Yes, you know, because you have drn. I am not writing one, and it basically means that integral over all position coordinates into what? UR1 to
Power minus.
e to the power of minus beta, but URn, isn't it?
Yes.
Divided by what?
DRN eta minus beta URN.
What is this? This is your z of n, isn't it?
Yes.
This is z of n. Now this one you can again write it as, see, I am just doing a trick. Same thing, dr1, dr2, ur12, n into n minus 1, dr n minus 2 whole divided by this quantity z and nothing. I just, this integral means dr1, dr2, dr3. So I wrote dr1, dr2, and then dr3 onwards I coupled, put them here. N into n minus 1 I put it inside and put ur1 to here. Okay, why I did that? Any idea why I did that?
We want G of R1.
Because again I look at carefully what is this quantity. And if you check your class notes, what is this quantity? This is your row 2 slash n, r1 comma r2. So the quantity is like that. So and then I can now write the whole thing as half dr1 dr2 row so this is fine. Is this fine?
Yes, sir.
Yes, sir.
Okay. So now after doing this, let us do a little more. Now I'll go a little fast. So what I'm doing, I'm calculating this. Is equal to n into n minus 1 and all this thing I did, sorry, is equal to half is there dr1 dr2. Let me write down one more time. Sorry, should be u. Something. Yeah. Just wait for a minute. This is u r12. Okay. Now what is the next step? I do this. Now this is going to be, you had this in one integral I can do actually v by 2, and then I'll have n by v, which is rho square of that, and I put dr12 g r12 u r12. So basically this integral dr1 dr2 I change it to dr1 dr112, and this one gives you v. This is exactly what I did. I have done it earlier as well. So what is this? If you put all together, you see that v it is going to be v by 2 into n square by v square. So this v and v will cancel partially. It will give you n square by 2v. And now what is n square by 2v? It is nothing but n by 2 into rho. This is actually equal to because I'm calling R12 as R, the separation. So this quantity you want to calculate is actually n by 2 times rho gr ur dr integral. Okay. So here is the physical meaning also. What is the physical meaning? It basically means that that there are, let me write down that there are 4 pi r square rho gr dear neighbors in a shell of radius r and thickness dr, isn't it? And the interaction energy and the energy of interaction between the central, the tack particle essentially, yeah, the central particles, and this is ur. Okay. So this is the average energy, it has to be, and since there are half factor is there because you have to take care of double counting. 1, 2 and 2 on they're identical. 3, 4 and 4, 3 they're identical. That's why the factor of 2. So basically 4 pi r square rho gr dr neighbors in a shell of radius r and thickness dr, and the energy of interaction between the central particle and the neighbor is ur. Okay, this is how it is. So your energy, average energy, if I divide by n, what I'm going to get? I'm going to get something like 3 by 2 kVt plus rho by 2 dr gr ur. This is very important result. Very important result. Okay, the same color it came. Yeah. Okay. Now, please note that I want to go a little fast here. The delta E by n is equal to del beta into beta delta A by n, because what is this? Delta E is something like your system minus your ideal gas system when there is no interaction. Okay, so what will be the delta E value? So I'm just thinking of a situation, I have an ideal gas kind of thing, no interaction, and then I turn on the interaction. Then what is the change in internal energy? In that case, since I do it very slowly, reversibly, so delta E has to be equal to delta A, because entropy change here is 0. Okay, there's no entropy change. So in that case, this is 3 by 2, I know, n kBt plus whatever I just did, n by 2 rho gr ur dr. What is E ideal? What is E ideal? Tell me, Kailash. What is E ideal for ideal gas?
3
It has to be 3 by 2 n kBt. So this one is going to be n by 2 rho g of r ur dr. Okay. So del E by n I can express as this. Is this clear? Is this clear? Del E by n I can express like this, because this will give me essentially delta A by n. Okay. What is, and also I can say that what is minus b delta A? It is nothing but ln q by q ideal. These are the partition function. Okay. So let us now concentrate on del E by n. Now this del E by n is equal to rho by 2, because this del E by n is rho by 2, integral of dr gr ur. Now low density case, when we are considering low density case. In that case, actually your GR is taken as exponential of minus beta UR. Why it is so? Because in general your WR, potential of mean force, would have two terms. What are the terms? Potential of mean force would have two terms. What are those terms? What are those terms? Those are UR and then delta WR. This is pair potential. And this and correction is, this is due to surrounding particles, isn't it? And if surrounding particles are low in density, what will happen to this? This goes to 0 at low density. So we'll do only low density case. In low density case, your WR is equal to UR. And you remember what is WR? It was minus KBT ln GR. From here you get this. So I can say what will happen to this integral, this one, I'm going to write it as rho by 2 dr exponential of minus beta UR into UR, and I can write 1 plus other terms which is a function of density. I hope you remember, understand what I am saying here. But these terms are negligibly small, so I can just neglect, but I'll formally write here. Just wait for a minute. Okay. So your rho by 2 into this integral, UR 1 plus whatever, this correction is very negligibly small, very small. It goes to 0. Okay. So essentially I have UR times exponential of minus beta UR. Okay. Now what I do here, I had delta. Okay. I had delta E by N. Let me write down again. Rho by 2 dr exponential of minus beta UR into UR. And other terms are there. Let me stick to this. Now, if you and this is equal to, actually, this is, if you go back to previous slide, the delta E by N is del beta of this. So basically you have del beta of beta delta A by N is rho by 2 dr. Okay. Now integrating over beta. What do I get on the left hand side if I integrate over beta? I get beta. Okay. What do I get? Anish, what do I get?
Delta A by N.
Yeah, I should get beta delta A by N. And on the right hand side, what should I get? What should I get? I have this dr UR. Then I also have, like, integrate from 0 to beta, and I change to dummy variable beta prime. What I get here is rho by 2 dr UR. This one you integrate, what I'm going to get?
Minus UR, minus 1 by UR, minus beta prime UR.
So I can say that minus, if I multiply minus on both sides, delta by n is going to be, let me write down, rho by 2 dr fr. Because this ur will cancel, no? And what is fr? Fr is 1 minus exponential of minus beta ur. Isn't it? Because when I put the limit, exponential minus beta ur minus 1, exponential of 0 is 1, isn't it? And they multiply with minus 1, that's why it is 1 minus this. So this is fine, the way the one I've written here. I can have other terms, other higher order terms, and then 0, negligibly small. I can have higher order terms, these are negligibly small. So this is how it is. Now recall, pressure is what? kVt d ln q by dv n comma t. This is pressure, no?
Yes.
It is start. And also remember, A is minus kVt ln q. So your pressure is actually minus del A del V n comma t, isn't it? The pressure is like that. What is P ideal? P ideal is rho kVt, no? Ideal gas equation. Rho is n by V, huh? Rho n by V, isn't it?
Yes,
Okay,
sir.
is this fine? So if rho is n by V, then V is n by rho. So basically this will give me that del V is minus rho square by n del rho. Fine? The del V is minus rho square by n into del rho. Okay, I'll use that. I'll use that in a minute. So what I'm going to do now is just calculate this quantity. Rho square, to finish in, I have just only few lines left. Yes, the rho square del rho beta delta A by n. This is equal to what? Rho square del rho beta by n, and delta A is what? A minus A ideal, isn't it? What will be the value? I take rho square beta by n outside. It is not del beta, sorry, del rho. Should have del rho of A minus A ideal. What will be del rho of A ideal? That you can put, because you know that P ideal is minus del A ideal by del V n comma t, so which is actually plus rho square by n del A ideal by del rho n comma t. So I'll just put it here. If I put it here, this is rho square beta by n del A del rho minus del A ideal by del rho. Okay. So now you know that del A del rho n comma t is going to be n by p square into p, and del A ideal by del rho n comma t is going to be n by p square into p ideal. So all these things you can express in terms of
And I
p
think
pressure.
that n by rho square.
N by
N by rho square, no?
yeah, n by rho square. I have written n by rho square. No, what is the problem? What I'm saying that this is so essentially this quantity is going to be rho square beta by n, and in here you'll have np by rho square minus n rho square into rho by beta. You can check this, and actually if you do all these things, what I'm going to get you rho square del rho of beta delta A by n is equal to beta p minus rho, and this gives you that okay, my beta p is equal to rho plus rho square, and what is this rho square into del rho of whatever beta delta A by n, and this is going to be rho plus rho square del rho of minus rho by 2 dr fr, because that was the expression. So this will give you rho plus rho square b2 by t, b2 function of t, and b2t is given by minus half fr dr. Fr you remember, and this quantity is called second virial coefficient. So you can check the algebra. I don't think it is a problem, but is the problem, the whole thing is okay, my pressure I can express as this rho plus, then what will be the so basically your beta pressure is rho plus rho square b2t. What will be the second virial coefficient for ideal gas? What is the second virial coefficient for ideal gas? Because u is 0, no interaction. U is 0 is 1, 1 minus 1 is 0, fr is 0, so bt is 0. And in this case, beta is 1 over kbt. So you take it on the other side, rho pressure is kbt times rho. This is actually what you have derived here is what? It's like virial equation. Isn't it? The virial equation of state for the fluid.
Yes.
This is exactly what I have done. So there is a lengthy algebra. Have a look. Anish, you are saying that there is some problem with somewhere. Can you tell me where?
So on the right hand side, where you written del A rho,
Yes.
that should be n by rho square into p, no? Because you've transposed that. So
This
that's
one.
you.
This one. This one
On
is
the
fine.
right hand side.
Can you see n by rho square? I have written there.
And it's looking like p square, and you had also mentioned p square. So
Sorry. Yeah, I should be more careful. Yes, it's p and rho. Thank you. You're right. But I think I put it correct, no? I put it correct, this one.
yes.
Yeah, that was just a... So anyway, we'll stop here. Very long class, because in the next class we'll talk about how to calculate this G of R and other things using MD simulation. Little bit of introduction, not much, very qualitative. And thank you very much for your attention. And now I will stop presenting and
Thank you, sir.
stop recording. Okay, thank you.